If we don't see a change in the size of the muscle as a whole, we shouldn't be fearful that there aren't changes occurring.
This is really the science behind what's going on as your body learns how to recruit muscle effectively as you begin strength training in order to experience the many benefits.
Welcome to the Strength Changes Everything podcast, where we introduce you to the information, latest research, and tools that will enable you to live a strong, healthy life. On this podcast, we will also answer your questions about strength, health, and well-being. I'm Amy Hudson. I own and operate 3 exercise coach studios. My co-hosts are Brian Sagan, co-founder and CEO of The Exercise Coach, and Dr. James Fisher, leading researcher in evidence-based strength training. And now for today's episode.
Today, we're going to be talking about a bombshell of a question. It's a big question for those people who are strength training with the goal of increasing muscle size. There's many people out there that want to look a certain way, want to build muscle, particularly in certain areas, and they want to know when they're strength training, why aren't my muscles getting bigger? We also see this in the context of people who are looking for certain body composition outcomes from their strength training as well. Maybe they come in and they realize how under-muscled they are. They need to gain more muscle mass, and they're aware of their muscle mass in relation to their body fat percentage, things like that. And so they may make a goal of increasing muscle mass. And after some time strength training, they may not notice a very significant difference in that muscle size that they're looking for or in that muscle mass. And so we're going to talk about how muscles grow today. We're going to answer the question, why aren't my muscles getting bigger? Particularly on my timeline. So Dr. Fisher is here to answer this question for us. We're going to cover a lot about this topic, and I hope it really encourages you and teaches you and opens your eyes to really how this works. Dr. Fisher, I'm super excited to dive into this topic today. Where would you like us to get started?
Yeah, so this is a great question. And it's been kind of probably the question, certainly by many males over the years, but by a lot of people who are engaging in strength training and are seeing that increase in strength. But historically, people have had this kind of idea that strength and muscle size are effectively the same thing. So muscles get stronger. Why aren't they getting bigger or so forth? So and it's a question asked by many trainers out there as well as many clients. So it's a great question to ask, and it's a really nice question to answer as well. So there will be a bit of science in this. It's worth clarifying at this stage. When this goes up on YouTube, there will be some slides and some images which will obviously help to clarify a few of the key points. You know, the old adage, a picture speaks 1,000 words. So we do encourage listeners, if things aren't clear the first time around, to maybe go and check out some of the slides on YouTube, or if you don't normally listen to YouTube or watch on YouTube, then maybe pause the podcast and have a look right now, and then you can see Amy and I talk through this topic as we go. So the question, why aren't my muscles getting bigger? Wow, what a great question. So historically, there's been this hypothesis presented from sort of the 1980s by a guy called Digby Sale. And the image is on the screen now, but just to clarify for the listeners, we've got time across our x-axis and we've got progress across our y-axis. And in progress, we've also got a number of different adaptations. And the 2 key adaptations that most people are interested in is strength and hypertrophy. Strength, of course, being how much force a muscle can produce or how much weight you can lift, and hypertrophy being an increase in the muscle size. Okay, but what we can also see on the figure is we can see a blue line that shows neural, or that's titled or labeled neural adaptations. And what we can see is early on, the curve for neural adaptations and the curve for strength adaptations run virtually parallel. What this means is that when we begin strength training, almost 99% of our adaptations or of our increases in strength on neural. It's our body's efficiency in producing force and even sustaining muscle tension and muscle force that is the key adaptation from strength training. And there's a big reason for this. Muscles are metabolically incredibly demanding to the extent where historically muscle's been talked of as, or muscle hypertrophy and muscle size increases has been talked of as a noxious effect of strength training, e.g., a negative effect. So we were talking about people want to get stronger, but they didn't necessarily want to add more muscle because adding more muscle demanded this extra calorie consumption and this extra kind of metabolic activity. So while some people do want to add muscle and muscle mass, and we generally say it's very healthy, other people, and it's great to think about kind of weight categories for boxers or martial artists or other sports, they don't want to add muscle. They certainly don't want to add muscle mass. They want to add strength and force production, but they don't want to add that extra muscle. So we can definitely think of these as two disparate adaptations to strength training. Now, if we carry on along that curve, what we see is the neural adaptations eventually plateau over time. But at some point, our hypertrophic adaptations, our increase in muscle size, will kick in, and an increase in muscle size can lead to an increase in muscle strength as well. Okay, so we've got this client and they come to the gym and they get stronger. And from the outset, their strength increase is almost purely neural adaptations. So let's talk briefly about those neural adaptations, if that's okay.
Let's do that.
So what we have is we can test the amount of motor units being recruited. So we've got to remember when we talk about neural adaptations, it's neurophysiology. It's the signals being sent from our brain through our alpha motor neuron in our spine out to our muscle fibers within the muscle. And we can test that within the labs with something called an interpolated twitch. And I used to do that in my physiology lab with my students. And it's a great example of how you can demonstrate this firsthand. But what we can do is we can say that most people can only recruit somewhere between 30 and maybe 90% of their muscle fibers. So there's all of these muscle fibers that are there, but when you send an impulse to those muscle fibers, you can't recruit all of them. You can only recruit some of them. Now, when you're very well trained, you can recruit most of them. Okay, so the example on the screen right now, which has force in newtons up the y-axis and time in seconds across the x-axis, shows that when somebody contracts their muscle, the force goes up. Okay, now what I didn't tell you is that what we used to do with our students is put a small electrical impulse across the length of the muscle. So we put an electrode at either end of the muscle, and we typically do this with the quadriceps or the biceps because they're the easiest, most accessible. And what we do is fire a small electrical current. And what that electrical current would do is recruit any remaining muscle fibers that the person hadn't recruited themselves. Okay. So you can see on the figure twitch 1, and you can also see twitch 2, and you'll see a slight peak where we fire those electrical impulses at twitch 1 and twitch 2. And that shows you that the force will go up with each of those two impulses. So this person is contracting this muscle as hard as they can. But even though they're trying to recruit as many muscle fibers as they can't recruit them all. So when we fire this electrical impulse, it recruits the remaining few, and so the force gets that bit higher. Okay, so that's an example of how we can assess how many muscle fibers are being recruited, or interpolated twitch technique. And if I now change the figure, I've put on a red line onto the figure as well. And our red line is for an untrained participant. So our red line now shows somebody who's never done any strength training before. So their neuromuscular system is much, much less efficient. They send an impulse from their brain to their muscle, but it really can't recruit many muscle fibers at all. So what we can see is that the force is much, much lower. But when we fire the impulse or the twitch, we see the peak reaches about the same point as it did for our person who was already strength training. And what we're saying is that both people have effectively the same number of muscle fibers and even the same muscle force capacity in this case, but one person was able to recruit those muscle fibers and voluntarily produce that force, but the other person wasn't able to produce many muscle fibers and therefore wasn't able to produce as much force. Any questions so far, Amy?
Yeah. So are is part of the neural adaptations that somebody is making when they just get started strength training, their body's way of basically learning how to recruit more muscle fibers when they exercise?
It's exactly that. It's called an increase in recruitment. And it's simply that they've effectively got these muscle fibers that are laying there almost dormant. And in fact, the tragedy in this is that if we get older and we don't use those muscle fibers and those motor units, the motor units can die. The motor units effectively become completely switched off. We effectively sever that mechanism from our neural system to those muscle fibers. Now, the great news is, no matter how old you are, you can re-innovate motor units. So you can recruit them in different ways. And there's two mechanisms of where you can do that. One, really brilliantly is called collateral sprouting. And that's where the surviving motor units extend new branches and so they reach different muscle fibers. So there might be a motor unit that already attaches to a handful of muscle fibers, but it can extend brand new branches of what's called axons out to the other muscle fibers to be able to recruit those muscle fibers as well. And with the other way that we can do that is something called axonal regeneration. It doesn't sound as exciting, and that's basically saying if the damage to the nerve is closer to the cell body, then the axon itself may be able to regenerate and reach those muscle fibers. So yeah, absolutely. One of our primary adaptations in strength increases is our ability to recruit muscle fibers or to kind of regrow those motor units.
And if you are a client of the exercise coach, your coach may have described to you the acclimation phase of your exercise journey. And this is really the science behind what's going on as your body learns how to recruit muscle effectively as you begin strength training in order to start to put yourself in the position to experience the many benefits that strength training offers, which I'm sure we'll get into later.
Yeah. Okay. So there are some other mechanisms as well of how strength increases. So the next one that's worth talking about is something called rate coding or firing frequency. Okay. And what this is saying is if we look at the figure on the screen, our untrained person is on the very left of the screen. Our trained person is on the very right. And I will explain this for those people listening on the podcast and not watching on YouTube. What we can see is basically a 5 series of fuzzy lines. They're like a graph where they show an impulse that goes up and then it's a bit of a fuzzy line and then it drops off again. And what we're saying is for somebody that's not trained, somebody that's not practiced in recruiting their muscle fibers, there's what's called an interpulse interval. And that is the time between that neural impulse being sent from our brain to reach our muscle fibers. And what we can see on the screen is that for our very untrained person, that interpulse interval is 50 milliseconds, which in the grand scheme of things is very, very long. A millisecond is only 0.001 of a second. But 50 milliseconds is a lifetime when we're talking about sending neural impulses. But as we improve our strength and as we engage in strength training, our interpulse interval drops down to around 20 milliseconds. So we can see that the line can reach higher, and we can also see that the line is now not so up and down as the impulse drops and then is actioned again and drops and is actioned again, but it's firing much more frequently. And we could also, in the same sense, we could also talk about this in terms of frequency, so the number of actions per second. So what we can see on the same figure is for our untrained person where there's a gap of 50 milliseconds, well, that's a frequency of 20 hertz, 20 actions per second. whereas our frequency for our trained person is now 50 hertz or 50 actions per second. So 50 times per second, your brain is able to send a neural impulse that's received by your muscle fibers to contract. And so this is called firing frequency, or it's also called rate coding. And obviously, our ability to send a sustained impulse to our muscle can help us to produce a greater amount of force or to sustain a force.
So, what this is really showing, just to summarize, is that the longer somebody strength trains, the quicker they're able to receive the neurological signals to their muscles to fire and produce greater force throughout the whole set more quickly than the untrained person. Would that be fair?
Yeah, exactly, exactly. The increase in force and the increase in ability to produce force is a product of our ability to send continued, sustained, and higher frequency impulses from our brain to our muscle fibers. If you can imagine trying to lift something and every uh, second you're not allowed to produce any force, you get off the ground and then have to put it back down again and get off the ground and put it back down again. Whereas if you continue sending that impulse with a higher frequency, well, now you can lift the object off the ground. So you're producing more force, but you're also producing a higher sustained force.
Makes sense.
And then really the other adaptation that we often talk about is basically how well we can group those motor units together and those muscle fibers together to perform any given task. And really, that's more about skill acquisition. So, for example, it might be a bench press or a chest press exercise, or it might be a leg press exercise. But we have to have a pattern of recruitment for our pectorals, our anterior deltoids, and our triceps, all the different muscles involved in that chest press, or our gluteal muscles and our quadriceps and our hamstring muscles for our leg press. So there's an improvement in that efficiency of how well we can recruit those muscle fibers um, in sequence and in synchrony to perform that task. And obviously that improves as a product of what I would call skill acquisition.
Okay, so that is a really great description of the acclimation process in that respect. That's really, really helpful. Thank you for that.
Yeah. And so all of those things, of course, lead to our strength increase, and there are neural adaptations. But so imagine that somebody's been carrying on strength training and they've gone through all these neural adaptations, and maybe they're still making small strength increases. But by this stage, they're thinking, well, I feel like my muscles should be getting bigger. Changes should be happening, and I want my muscles to be getting bigger. So what else is happening? Well, to do that, or to understand that, we have to think about, or we have to have some understanding of how the muscle exists. So I put an image on the screen there that shows our client. In this case, they're doing a bicep curl, and it shows their muscle fascicle, their muscle fiber within the muscle fascicle, and their myofibrils. So you can see there are multiple muscle fascicles within a muscle. There are multiple fibers within a fascicle and multiple myofibrils within a fiber. And a great way to think about this is to think about the different levels of structure. So we can think of things at a macro level. We can look at the muscle and we can see the change in the muscle itself. We can look at things at a micro level where we can look under a microscope and look at the fascicle or the muscle fiber. And we can look at things at an ultrastructural level where we can look at maybe the muscle fiber or even the myofibril and look at the very, very small changes that are occurring. And once we start to realize the variance and the degree of sort of size of these structures, we can start to see that even a 1 or a 2% change at a myofibrillar level doesn't equate to a 1 or a 2% change at a whole muscle level. And so forth all the way up. A small change here equates to maybe a smaller change at the next level, and so on. So what we can talk about is first of all, how myofibrils can increase force production. So our myofibrils, as we said, were our smallest level there, and each myofibril contains our actin and our myosin filaments, and they cross over each other. They effectively grab hold of each other to pull to produce force. So if we do see an increase in myofibrils, which we want, or an increase in the size of myofibrils, that also equates to an increase in the number of actin and myosin filaments, and that equates to an increase in the number of cross bridges per muscle fiber. So more cross bridges between actin and myosin equals more force production. So that can be key in how strength can increase. So let's talk briefly for a second about what can happen at a myofibrillar and even at a myofiber level. Myo simply, of course, means muscle. So if we're talking about myofibril, we're talking about a fibril within a muscle. If we talk about a fiber or a myofiber, we're talking about a fiber within a muscle. That's all. Okay. So this is the image on the screen is a great image by Jorgensen et al. From 2020. And I've put the reference up there if anybody wants to go and find the research paper. And what we're showing here is that our fascicle containing our muscle fibers or our myofibers, when our myofibers grow, our muscle fascicle grows to allow that growth of muscle fibers. And then the second example below that is what's called hyperplasia. And that's saying that the myofiber the muscle fascicle, can increase in size if the myofibers split and form an increase in number. So hyperplasia is an interesting concept. We talk about hypertrophy as an increase in size and hyperplasia as an increase in number. There is some evidence around hyperplasia, but many people have kind of still questioned whether it truly exists. There's not a huge amount of evidence around it in human models. There is more evidence around it in feline and rat models. So we know it exists in the natural world. We're not completely clear if it exists in human biology. But when we look at the image, what we can see is that the changes are great on an image. The circle that represents the fascicle has simply increased in size. The circles within the fascicle that represent the muscle fiber have increased in size proportionately as well. But what we can also see is the space around the muscle fibers within the fascicle has also changed. That's also gone up with it. Now, what we don't know is whether that happens to that extent. What would be fair to assume is that some of that sarcoplasm, the sarcoplasm is basically the juicy bit around the muscle fibers within the muscle fascicle, is some of that sarcoplasm is effectively kind of squeezed out and the muscle fibers take up more of that space. So what we can actually see is the muscle fibers increase in size or increase in number, but without a change to the size of the muscle fascicle. And if anybody is following me on YouTube, then you'll see that I've kind of shown this on the next image. The next image, just for listeners, it shows a circle and it shows 4 muscle fibers within it. And it shows the rest of the space being taken up by sarcoplasm. But what we've said here is, imagine now the muscle fascicle doesn't change in size, but the muscle fibers get bigger. They just take up more of that sarcoplasm. Or the muscle fascicle doesn't change in size. There are just more myofibers within the fascicle. Okay, so this can happen at a myofibrillar level within the muscle fiber, at a myofiber level within the muscle fascicle, and potentially even within a muscle fascicle level within the muscle itself, that effectively there is just a greater packing density within the muscle. And this is something that we kind of use as a bit of a throwaway term of muscle quality, which effectively is the amount of force that somebody can produce per size of their muscles. So somebody that has, let's say, average size muscles, but is very strong, has arguably better muscle quality than somebody who can produce the same amount of force, but has much, much bigger muscles. I'm going to pause for a second there, Amy, because I know that you have to jump in and help give this explanation to the listener. So what have I not done? What have I missed?
No, first of all, if you're not following along on YouTube, you should go to YouTube immediately and watch this presentation. I'm looking at a slide right now that just shows 3 circles that are the same size, and it just is a very helpful descriptor of what's going on inside the same size muscle is great. The muscle itself looks the same size from the outside, but there is so much going on the inside of the muscle that's causing the person to be able to be stronger, produce more force, and all of these other things. So the muscle is a better muscle. It's a more capable muscle for the size that it is, which is actually a very positive thing. It's a denser muscle. So muscle density is what your body wants to do first. Add density to the muscle for the same size to increase your ability to perform without increasing volume, because what Dr. Fisher mentioned before is that larger muscles are more metabolically expensive. And so this is a great way to picture scientifically what's going on and why your body wants to do that. It's a really cool way to understand it, and it's super encouraging. It's just easy to look to externals as the way to understand if I'm making progress or not. But so many times we can see that we're making strength progress. We're stronger. We feel stronger, even though the muscle from the outside may look the same. And this is why.
Yeah, great points. Great points. Thank you for giving it that clarity, Amy. So one of the key things that I talk about when I do this kind of lecture is I say, if we don't see a change in the size of the muscle as a whole, we shouldn't be fearful that there aren't changes occurring. There are absolutely changes occurring. I often talk about this as the morphology of the muscle. There are morphological adaptations occurring within the muscle. There are structural changes occurring that are improving the quality of the muscle. So as we age, one of the key things that we talk about when we talk about muscle mass is actually the muscle quality and the muscle density, as Amy said. And the other thing that we can think of in terms of this is actually mass. So we're not talking about a huge change in body mass, but if you can imagine that somebody steps on the scales and their muscles haven't got bigger, but their body mass has gone up, they might think, wow, I've put on weight. Whereas actually, they've simply increased the density and the mass of their muscles. And I mean, we're talking about such small margins, they probably wouldn't see a large increase in weight. But if somebody is really tracking their weight to the nth degree, then they might see these changes. So one of the other things that we can think about in terms of looking at muscle changes is the measurement type. So we have a couple of different types. The first is called in vivo, and that's it within the living. And that's a whole muscle measurement. So we typically use something like an ultrasound. In our labs, we used an ultrasound, or you can use an MRI, magnetic resonance imaging, or computerized tomography, which is a CT scan. And many people will have heard of those in the medical context. So a scan of the body. Or we can look at muscles in vitro, which is technically in glass. And that's by muscle biopsy, where we would use a needle and we would remove the muscle cells from a person, and then we would stain them and look at them under a microscope within a Petri dish, and hence within glass. And one of the key things about this is that they don't show good agreement between the two. So, for example, if we look at a muscle biopsy, where we're simply looking at the size of the muscle fiber itself, then in some studies we've seen around a 16 to 30% increase. But if we look at the same muscle from an MRI, we only see a 7% increase in the whole muscle. And this is a perfect example of how we can identify that there is a change in the muscle fiber packing density. We know that the muscle fibers have grown by 16 to 30%, which is relatively large, but the whole muscle has only changed by around 7%, which is actually still relatively large in the grand scheme of things, but interestingly, might still not be identifiable to the naked eye. So knowing that there are different ways in which muscle size is measured can be a key marker of telling us that we know that packing density can change. Something else that we can think about is the muscle architecture itself. And this is maybe a bit less important, but I think it's still interesting, and I always try and tag it onto the end of this conversation. Our muscle fibers don't always run in the same direction. We typically think that they run from one joint to another joint. So if we think about our biceps, we imagine our muscle fibers in our biceps running from our shoulder joint to our elbow joint, and that would be called parallel. And that's exactly true of our biceps, actually. But in other places within the body, our muscle fibers don't run from one end of the tendon to the other end. They actually run at an angle. So, for example, our vastus lateralis on the outside of our thigh is a pennate muscle. And that means that there's an angle of pennation, that the muscle fibers actually run diagonally across the muscle. So, and what that means is that there's a tendon and what's called an aponeurosis that runs effectively 3/4 the length of either side of the muscle that allows those muscle fibers to run at an angle. Now, of course, if you're watching this on YouTube, you can see the image up there, and you can see that the next example is also bipennate muscle fibers, where the muscle fibers almost run like a leaf. There's an aponeurosis that runs straight down the middle of the muscle, and the muscle fibers spread out either side of that aponeurosis. If you're not watching on YouTube, then as I said, a picture speaks 1,000 words, but hopefully that description has helped a bit. So when we talk about the pennation angle, we know that this also changes with strength training, but it also means that we can measure the muscle in two different ways. So the image on the screen now is an ultrasound image. And what we can see here is, for anybody who's not watching on YouTube, I'll describe it as best I can. It's a very sort of gray, out of focus image, because that's what an ultrasound typically looks like. They're not perfect clarity. As you can imagine, an ultrasound is sending sound waves into the body and receiving those sound waves as they bounce back from things. So imagine, if you're old enough, an old black and white television picture that's really not very clear. But we can see kind of a mottled white line near the top, and that is our skin and our subcutaneous fat. So we put the ultrasound against the skin, and it obviously reads the skin and the fat first of all. And then below that, we can see these kind of white lines that are a bit faint, that are a bit more faint than the skin and the fat, running at an angle. So they're not directly perpendicular to the skin or the fat, and they're not parallel to it either. So what we can see from our ultrasound is we can measure muscle thickness, which is the anatomical cross-sectional area from the skin or the fat down to either the next muscle or down to the bone. And that's exactly what it's called. It's called muscle thickness. And that's marked on the image with an MT. But we can also measure what's called physiological cross-sectional area, and that is the thickness of the muscle if we measure it perpendicular to the muscle fibers themselves. And that's shown on the image with a red arrow. So what we can see is, if we consider the angle of pennation, which is shown on the image again, but if we consider that the muscle fibers aren't running parallel and they aren't running perpendicular, they're running at a slight angle, then my red line is now longer when I measure my physiological cross-sectional area perpendicular to the muscle fibers than my muscle thickness or my anatomical cross-sectional area, where I measure it perpendicular to the muscle belly itself.
Wow. So it sounds like there's a lot of ways to look at this. And I guess my immediate question is, what is the most reliable measure? What's the most meaningful measure here for the average person?
So there's no answer to that. There's no answer to
Yeah.
that. Most people are probably interested in how their muscle changes from looking from the outside in. And interestingly, I always, I was a young guy doing strength training many, many moons ago, and I was interested in bigger muscles, and that was a big part of why I was strength training. Um, but the reality is that, to some extent, strength training is wasted on people that just want bigger muscles. It's a very superficial acceptance or adaptation to strength training. If we think about all the health benefits that we've talked about extensively on this podcast, and then we talk about some of these morphological adaptations and neural adaptations that are increasing strength, then to think that we're only interested in having a bigger muscle at the end of the day, we're missing so much of what's happening within the muscle and within our neuromuscular system and from our health benefits. So, of course, if people are interested in muscle thickness, then they're only really interested in the anatomical cross-sectional area of the muscle. Whereas actually, if people are interested in a bit more than that, then there's no real best way to measure. There's just different ways to measure, and the different ways of measuring can show us the changes that occur. Now, the point in talking about this pennation angle is, as we said earlier on, is the pennation angle can change with strength training. And the reason that it changes is because when you have a pennate or a bipennate muscle, the angle that the muscle fibers run at, as it changes, it can produce more force. So there's kind of an optimal angle for the muscle fibers to be able to pull that can produce the most force. So our muscle fibers will make that adaptation, which will help to make a strength increase long before they will add muscle mass or muscle size, because that is metabolically expensive, whereas this is just a slight structural change. If you imagine building a house, this is like saying, oh, I can just lay my bricks in a different way. I don't have to get tons and tons of new bricks. So we're simply just changing the structure within the muscle. We're making it far more efficient, far more effective as we go.
Cool. That's cool.
So to summarize all of that, we can say that resistance training can cause an increase in the pennation angle, which is what we just said. An increase in pennation angle can equal an increase in force production. An increase in pennation angle also allows an increase in the number of myofibrils per muscle fiber. Okay, because the angle has changed, so there's effectively space that's now freed up. And so we can now add more myofibrils within the muscle fiber, or more muscle fibers within the muscle fascicle. And that can equal an increase in what's called our physiological cross-sectional area, which was our measurement of the thickness of the muscle perpendicular to the muscle fiber. But it has absolutely no change to the anatomical cross-sectional area, which is the whole muscle. And that's key, that we're not seeing those changes. So the summary, and this is maybe the key part that everybody's interested in, is we can have myofibrillar and myofiber hypertrophy and or hyperplasia. And sometimes that leads to bigger muscles, and sometimes it doesn't lead to bigger muscles in the short term, but it can lead to a greater packing density of myofibrils and myofibers within their respective myofibers or muscle fascicles. We can also see a change in pennation angle, and that can also lead to a greater packing density. And ultimately, we can see a change in what's called the physiological cross-sectional area, the measurement perpendicular to the muscle fibers, but not the anatomical cross-sectional area, which is the muscle as a whole. Now, there's a couple more really quick points to touch on. First of all, we don't see the same growth in a muscle all the way along the muscle. We might see the proximal, which means that the nearer part of the muscle grows sooner. We might see that the distal part of the muscle grows sooner or grows bigger, or the mid part grows bigger. So we don't see the same amount of growth at different points within a muscle. And then the other key point that we can think about is that muscles around the body grow in different ways and at different rates. So there was an image from a research paper a number of years back, and that showed that, for example, in some people, the quads had the capacity to grow sort of 20 to 30%, but the shoulders only had the capacity to grow between 5 and 15%, and so forth around the body. And obviously, there's a large degree of variation around the population in that growth adaptation as well.
Yeah. Yeah. So if you're strength training, that's important to keep in mind, is that you can't just point to an area of your body and say, this is the muscle I want to grow, no matter what my genetics say, right? You will have the proclivity to be able to add muscle in certain places quicker than other places, just like how fat loss works. It's the same concept, right? So
Yeah, exactly. And of course, if we want to add muscle in a certain place, then we do have to stimulate those muscles. So if I want to add muscle in my biceps, then I can do a row exercise, I can do a pull down exercise, both of which will use the biceps, but I can also now do a bicep curl exercise, or variations of a bicep curl. So as long as I'm getting the stimulus, then I should be stimulating some form of adaptation. But yeah, just because you've provided that stimulus doesn't mean they're suddenly going to grow bigger. When people think about strength training, I still have this image in my head that some people think that you go to the gym, you start strength training, and it's like the 1970s TV show, Bruce Banner turned into the Hulk and all his clothes ripped, the muscles grew huge, and you became Lou Ferrigno. Lou Ferrigno was a world-class bodybuilder, and muscles don't grow that big. So
Very true. So, if you're listening to this podcast and you're somebody who strength trains and you have had the tendency in the past to get discouraged because you didn't see growth in a very specific way that you wanted to see growth, Dr. Fisher, what would you say to that person to encourage them along the way in their strength training journey?
yeah, so first of all, there's a few things that can impact muscle growth and muscle adaptations as a whole. First of all, you have to apply the right stimulus. So strength training has to be key. You have to have the right nutrition. So you have to have protein to build muscle. We've talked on a previous podcast about the amount of protein. So many people probably drastically underestimating the amount of protein they're consuming or under consuming the amount of protein needed to build muscle. And then, of course, you need to sleep. Our strength training is our stimulus, but our muscle grows during the adaptive phase in between stimulus. So you have to go away and get good quality sleep. So I often talk to people that are, lawyers or high-powered businessmen, type A business people who really, really love their strength training, but they also will burn the candle at both ends, and they kind of talk about having 3 or 4 hours sleep a night and having to skip meals because of these meetings or the amount of work they have. And then they ask why their muscles aren't growing. And I sort of say, hey, the strength training part you've ticked, but everything else is suboptimal. So those two things are really key to kind of tick the boxes to create some increases in muscle size and muscular adaptations.
Okay, so good, so good. So much to think about and so much to chew on from this episode. Thank you so much for breaking all of this down for us, Dr. Fisher. I just think it's very, very helpful. If you're a trainer out there, please use this information to encourage clients. If you're a client out there, if you're somebody who's strength training, please take this as a win, as an understanding of, man, no matter what I see happening on the outside, as I continue my strength training journey, there are so many good positive adaptations happening on the inside. Watch or listen to this episode 5 times if you have to understand that and to reinforce that because you don't want to quit. Um, Great. Well, any other closing comments, Dr. Fisher?
Actually, I do have one final closing comment. We talked on a previous podcast that there was a paper that I talked about called "There Are No Non-Responders to Strength Training," and I think it's really important to kind of highlight that paper once again. And in that paper, it was a study where a group of older adults engaged in strength training, and they all improved in at least one parameter, whether it was some of the functional capacity tasks, whether it was an increase in muscle size or muscle strength or muscle mass. So the key thing is not to be disheartened by engaging in strength training and not seeing the one adaptation that you might have been most interested in, is to engage in strength training with the confidence of the positive adaptations that you're creating for your body.
Exactly. Yep. Talk positively to yourself, people. Remind yourself of those things. Don't discourage yourself. Very good stuff. Well, we will see you next time on the podcast, and we hope you remember strength changes everything. Thanks for listening. If you enjoyed today's episode, please share it with a friend. You can submit a question or connect with the show at strengthchangeseverything.com. Join us next week for another episode, and be sure to follow the show on Apple Podcasts, YouTube, or wherever you get your podcasts so that you never miss another episode. Here's to you and your best health.